I separated out those two into two lectures because the way that maybe you can think about duality in linear programs is a very special case of duality where we can actually kind of mathematically construct the dual in a way that tries to get the criterion as a linear combination of the constraints. So that's what we did last time. We try to play with the constraints until we can get, say, a lower bound on the criterion if we have a minimization problem. And I like that perspective of duality in linear programs. I think it's very transparent. Duality in general programs, in general convex problems, is not done the same way. It proceeds with a kind of different flavor. It actually ends up being equivalent to what you saw for LPs, but it uses a technique that we call the Lagrangian. We form what's called a Lagrangian. So we'll go through that today. And I'll just emphasize again, just because why not, that I think duality is just a very beautiful subject. And so this is personally one of my favorite parts of convex analysis. I think it has a lot to offer. So just to give you a refresher, last time we talked about duality in linear programs. This was our kind of generic form LP we thought about examining. So minimize C transpose X subject to some equality constraints X equals B and some inequality constraints Gx less than or equal to H. And we saw that corresponding to this linear program, which we called the primal in the context of this relationship, the primal problem or the primal LP, we had what was called a dual LP. And that was the following. It was a maximization problem. And we maximized the criterion minus B transpose U minus H transpose V. So U and V are now our optimization variables. They're called the dual variables. And the constraints we had were, again, equality and inequality constraints. Equality constraint was minus A transpose U minus G transpose V is C, and V is bigger than or equal to 0. OK, so a few high-level things. For any U and V, where V is positive, we saw that plugging in such a U and V that were feasible gave us a lower bound on the primal problem. So if I give you U and V that satisfy V being positive and this equality constraint, then if I evaluate the criterion here, that lower bounds the optimal value of the primal problem, primal criterion. And we actually argued that, or at least we saw it in certain cases, and I told you that many times what's going to happen is that when you actually maximize the dual problem, you're going to get the same value as the optimal value of the primal problem. Okay, so this gives us a lower bound for any feasible U and V, but when you take the tightest lower bound, it's going to actually equal the primal criterion. And the way we saw that we formed this was that we defined a dual variable UI for every equality constraint, AI transpose X is BI. And we defined another dual variable, say Vj, for every inequality constraint. Gj transpose X is less than or equal to Hj. And we looked at them as multipliers. And we took linear combinations of this equality constraint. When we look at this as Ax minus B is equal to 0. And of this constraint, when we look at this as Gx minus H is less than or equal to 0. And we saw that just by virtue of the fact that this thing was going to be negative or 0 at best for a feasible point X, and each of these were constrained to be positive, this guy gives us a lower bound on the right. So this is always less than or equal to 0. This is what we saw, right? Just by virtue of the fact that, like I said, this is going to be less than or equal to 0 for a feasible point X. That's positive, and this is 0. And we rearranged this to get something transpose X is bigger than or equal to something else. And we declared that if this happened to be equal to C, then we got a lower bound on our primal problem. So that was the basic idea of duality in LPs. Right? And that's how we formed this dual problem. Okay, so if we set C to be equal to this leading factor here, minus A transpose U minus G transpose V, then we get a lower bound on the primal problem. That was explanation number 1 for the dual. Explanation number 2 is the one that we're going to kind of carry forward today. And that was slightly different, which is that if we look at the same linear form here, this guy here, because it's less than or equal to 0, if I add it to the primal criterion, so if I take C transpose X and then C transpose X plus that linear form, I can only have made the right-hand side smaller because it's less than or equal to 0. Okay, so it starts off with the same kind of observation. And now we just define this function, which is now a function of primal and dual variables, so x, u, and v, to be something we call the Lagrangian, L of x, u, v. And because L of x, u, v is always a lower bound on C transpose x when x is feasible, if we were to minimize C transpose x over the feasible set, which gives us f star, then that has to be bigger than or equal to minimizing the Lagrangian over all feasible x, right? Just because of that inequality we established, which is in turn bigger than or equal to what happens if we minimize over all x the Lagrangian. So this is kind of the key step in this dual explanation. We can forget about the primal feasible set, and it still gives us a lower bound. And this we define to be just a function of u and v, which we call g. G is now called the Lagrange dual function in this relationship. And this g, it turns out for that last problem, if you have a linear program, is exactly the same as the criterion we would have formed in the dual from the other explanation. Okay? It ends up being basically just the criterion that we already had, minus b transpose u minus h transpose v, subject to a constraint that c must be equal to minus a transpose u minus g transpose v. So both explanations arrived at the same dual problem. They just had a different perspective in doing so. Okay, the reason we like the second one now is that it's actually completely general, and we're going to see that it applies today to arbitrary convex problems, not just linear programs. Questions about that? Okay. So there's the outline for today. We'll talk about Lagrange duals, the concepts of weak and strong duality, go through some examples, and then we'll give a preview of some of the uses of duality. So we'll have another lecture after the one that comes next. So next we'll talk about the Kkt conditions, and then we'll have a last lecture on duality that talks about all the uses of duality, and we'll just give a bit of a preview of that at the end of today. So here's our setting for today. Let's consider this general minimization problem. Right? This is the kind of general form of an optimization problem we saw at the very start of the class. Minimize some criterion function f subject to a bunch of inequality constraints. Hi of x is less than or equal to 0, and equality constraints. Lj of x is equal to 0. I'm actually going to say outright that this problem doesn't need to be convex. So the discussion of duality actually extends to even non-convex problems, general optimization problems. We'll see where things kind of will become complicated with non-convex problems later in the lecture. But at least for now, we don't need to think about this problem as being convex. It's just an arbitrary optimization problem. Of course, like I said, we'll pay special attention to the convex case because it ends up being, the duality relationship ends up being stronger typically in that case. So from this problem, we define a Lagrangian, which is just the same thing we did with the linear program setting, but with these constraint functions instead of linear ones. So we define a pair of dual variables u and v where we have one ui for every inequality constraint. Oh, well, I hope this doesn't confuse you too much. I actually use slightly different notation here than I did with linear programs. Before I had u multiplying the equality constraints, and now I have it multiplying the inequality constraints. It doesn't really matter, of course. But that's why we have this constraint that u is bigger than or equal to 0. So I defined one ui for every inequality constraint hi of x is less than or equal to 0, and one vj for every equality constraint lj of x is equal to 0. And I formed a Lagrangian, which is the criterion function plus linear combinations of the constraint functions with the coefficients ui, and linear combinations of the equality constraint functions with the coefficients vj. Okay? And the implicit domain of this Lagrangian over u is that u should be bigger than or equal to 0. So we can just think about it as if we happen to pick a u that's smaller than 0 in any component. So that should actually say, that statement should actually say L of x uv is equal to minus infinity whenever u is not bigger than or equal to 0. So if any component of u is negative, then we can think of just the Lagrangian as being minus infinity. So So what's the important property of the Lagrangian? It's just what we saw with linear programs, but of course it holds here as well. At every feasible point x, provided that we are at points u and v in the domain, right, which means that u has to be bigger than or equal to 0, at every feasible point x, the Lagrangian provides a lower bound on the criterion value, primal criterion value f of x. Okay, that's just because, really with the same logic as before, for a feasible point, hi of x is less than or equal to 0, ui is bigger than or equal to 0, and vj is anything but lj of x is equal to 0. So this entire term we added is at best less than or equal to 0, and so it's less than or equal to f of x. Right? The Lagrangian is less than or equal to f of x for feasible points x. So here's just a pictorial example to show you what the Lagrangian looks like. See if I can blow it up for you. So in this example, the criterion function is this guy, the solid line. That's f of x. And we have only one constraint. It's an inequality constraint. And that's that this function, which is called h of x, must be less than or equal to 0. And so if we look at that constrained region, it ends up being an interval from about, I don't know what the axes say here, maybe minus about minus 0.5 to 0.5. Okay, so we're trying to minimize this solid line subject to our argument lying in that interval. That's f of x. And what I've drawn here are, in each dotted line, is the Lagrangian as a function of x for a different Lagrange multiplier value, u. Okay, so each dotted line corresponds to the Lagrangian as a function of x for a different value of u. Each u here, right, has to be bigger than or equal to 0 because we have an inequality constraint. And what is the claim? The claim is that no matter which dotted line I look at, no matter what that value of the Lagrange multiplier, the dual variable u is, that function that I formed is always a lower bound on f of x over the feasible region. Okay, and that's certainly true. Right? Every dotted line, think of it as a Lagrangian as a function of x for some u, it certainly lower bounds the primal criterion f of x here. Now it's important to acknowledge, though, that that's only over the feasible region. Right? It's not everywhere. You can see actually outside of the feasible region here, we actually have the Lagrangian being bigger than or equal to our criterion function. That's because here h of x is actually bigger than or equal to 0. So we get the opposite direction in that inequality. So just over the feasible region does it actually lower bound our criterion function. Okay, so just a picture to visualize that. Let me pause for a second. If there's questions. Okay, so kind of the natural extension of the Lagrangian is the Lagrange dual function. So it's defined by minimizing the Lagrangian over all points x, not just feasible ones, all x. That's a very important distinction. So simply by virtue of the fact that L of x is always smaller than or equal to f of x when x is feasible, if we minimize them both over the feasible set, we get this inequality. Right? F star, which is the minimum of our criterion function over the feasible set, which we're calling C, is bigger than or equal to the minimum of the Lagrangian of the feasible set. That just comes from that previous inequality we established pointwise. And this is a very important step. If we throw away the primal feasible set and say, hey, I'm just going to minimize the Lagrangian over all x, we still get a lower bound, right? Because I'm minimizing over a larger set. The value of the function I'm minimizing can only go down. And we define this latter guy, right, which has no appearance of x anymore because we've minimized it out, to be GUV, which is called the Lagrange dual function. Okay? So why this is so important is that almost always, in fact, I can't think of an example where this is not true, you're not going to be able to analytically minimize the Lagrangian over x in the feasible set. Right? That's about as hard as actually solving the original problem, pretty much, because you've restricted x to be in the feasible set. Now you're trying to minimize a function which is not only the criterion, but plus a bunch of other terms. So forming this as a function of u and v, had you decided to stop here, is typically, I'd say generically, not possible analytically. Okay, you just can't write down what that function would be. However, because constraints often complicate the nature of minimization, it's much more typical that you can form this function analytically. So for a lot of examples, once we throw away the constraint set, we can form what we call the Lagrange dual function explicitly as a function of u and v. I can write down a mathematical expression for what it is if you were to tell me the criterion function and the constraints. Okay, and this of course, just we can see from this relationship, it has the important property that if we take any u that's non-negative in each component and any v whatsoever, these are called our dual variables, then f star is bigger than or equal to g of uv. Okay, and we actually call this the set of all u for which uv for which u is non-negative and v is anything dual feasible points uv. Okay, for that reason, exactly. So here is another example. Here we've looked at, it's actually the same example, it's just in a different kind of perspective. This dashed horizontal line is the primal optimal criterion value. That's f star. Okay, and what I've drawn here is the Lagrange dual function as a function of there's only one dual variable here, right? Because we had only one inequality constraint here that was given by this dotted function. And it's drawn as a function of lambda in this plot. That lambda is our u. Okay, so think of this as the Lagrange dual as a function of u, which is the only dual variable. And sure enough, for any value of the dual variable, which is bigger than or equal to 0, it lower bounds the primal criterion function. It's exactly what we were told happens as a result of this relationship. What do we notice here, actually, that's kind of note? Yeah. Not a tight bound, right. So if I maximize the dual, then what happens is actually I don't quite get f star. There's a little bit of a gap there. So that's called a non-zero duality gap. Why does that happen? Like at a very high level, what could you guess based on this picture why that happened? What was the note about the problem here? What's the note about the primal criterion, for example? It's not convex, right? So we're going to see that strong duality is actually very closely tied to convexity of the problem you're looking at. Okay, so this is just a kind of a preview or teaser of what's to come. Here's a less of a toy example. Let's drive the dual of a quadratic program. So we already saw duals of linear programs. Here's the dual of a quadratic program. This is the QP we're looking at. It's a standard form QP. Okay, so 1/2 x transpose qx plus c transpose x subject to the standard form constraints, where q is, in this example, it's positive definite. So it's strictly positive definite. Its lowest eigenvalue is bigger than 0. So we just go through the mechanics. Let's just follow the prescription of duality. We're going to define a Lagrange dual variable v corresponding to every component of that equality constraint, ax equals b. And we're going to define a Lagrange dual variable u corresponding to every element of that inequality constraint, x is bigger than or equal to 0. And we'll form the Lagrangian for our QP, L of x, u, and v, which is equal to the primal criterion, f of x, plus the sum of ui times, well, we usually think of the constraint functions as hi of x is less than or equal to 0. Here hi is actually minus xi, right? So it's times minus xi plus the sum of vj times aj transpose x minus bj. This is our constraint that lj of x is equal to 0. And I've just written that succinctly in the slides as minus u transpose x plus v transpose ax minus b. It's just easier to write it that way. Okay? So now it's our job, after having formed that, to minimize this over all x. Not over the x that are feasible, but over all x. That's the important distinction here, right? You can see that if I told you to minimize this function, where f is this quadratic, over the constraint set, you wouldn't know how to do that. That would be about as hard as the original QP. But minimizing it over all x is actually not hard, because this is just another quadratic, which we know how to do explicitly. Okay, so that's what we've done here in the slides. Let's just carry through the calculations a little bit more detail on the paper. So f of x was 1/2 x transpose qx plus c transpose x plus all this stuff. And now let's just group everything that multiplies x. We only have one quadratic term. That's this leading guy. Then we have a bunch of stuff that multiplies x. I guess it's convenient to write this as c minus u plus a transpose v transpose x. Sorry? Oh, this is a plus, right? And then everything else that's left over, which is just minus b transpose v, I suppose. And now our task in forming the Lagrange dual function, right, which is g of uv, it's the minimum over all x of Lx uv, is just to minimize this quadratic as a function of x. And what's the minimum? Let's just do a little side note here. If I gave you the quadratic, so I guess I like to start simple. Ax squared plus bx plus c. What's the minimizer here? I just always remember this. It's minus b over 2a. So now if I were to give you this quadratic, which is really just a higher dimensional version of this guy, it's again minus b, whatever multiplies x, over 2a. But a here is a matrix, so I write it as q inverse. So the minimizer is just q inverse times minus b. Okay. I could have also gotten this by just differentiating and setting equal to 0, but I think this is a helpful kind of memory tool for me at least. And if we plug in the minimizer, you can see we're going to have minus 1/2. No, sorry, we're going to have 1/2 of that term here, 1/2 of this transpose q inverse this here, and we're going to have a full minus 1 of this transpose q inverse here. So what comes out is just a total of minus 1/2 times b transpose the, I'm calling this term b, c minus u plus a transpose v transpose, the inverse of the quadratic form transpose itself, and then this was left over. Right, this minus b transpose u is left over. Okay, so that is an explicit formula for our Lagrange dual function. And a pretty non-trivial conclusion, right, which you probably wouldn't have guessed by looking at it, is that for any u and v, where u is non-negative in each component, the value of this is always going to be less than or equal to the value of that qp up there. Okay, it always lower bounds the optimal value in that primal problem, f star. Okay, here's an example with the same problem, but where q was positive semi-definite, not necessarily positive definite, which means that it didn't have an inverse. And I guess I'll just probably not go through this. You can go through it. It's the same calculation. You just have to account for the fact that q is non-invertible. So if you were to minimize this over x, and a certain null space constraint on q wasn't met, you would get minus infinity. So basically all that happens is it introduces another constraint into the dual. It has to do with the null space of q. Because q is non-invertible, it can have a non-trivial null space. Okay, so you can go through that on your own. The quadratic program you get out at the end of the day is basically, or the dual function is basically this one with this replaced by q pseudo-inverse. So the pseudo-inverse of q. And its domain is just a bit restricted. So here's a quadratic program in 2D. Now approaching the notion of, we're going to talk about weak and strong duality. And what I've done just to visualize is I've defined a quadratic function in two variables subject to the constraint that x must be bigger than or equal to 0. And I've plotted the quadratic function over the positive orthant. So for the interpretation of this like upper surface, think about this as x1 and this is x2. So I've looked at the positive ortho, I've plotted it. That's the quadratic I'm trying to minimize. And I've drawn the minimizer actually, and it's a red dot, and the minimum value is a dotted line. And it was a very simple quadratic. It's just a quadratic in two variables. I was able to here in this example, just like as a special case of the last one we went through, form the quadratic dual function analytically. And the reason I chose to have this constraint x bigger than or equal to 0 in this example was that, well, the dual is going to also have the constraint that its variables, u, must be bigger than or equal to 0. So I could plot them on the same graph, right? Because I have two constraints, x1 bigger than or equal to 0 and x2 bigger than or equal to 0. So I have two dual variables. And because by nature of the fact that they're dual variables for inequality constraints, they're always constrained to be non-negative. And so now I've plotted the dual surface in the same plot. Now for this function, I interpret the axes as u1 and u2. It's two variables. And I've drawn its minimizer in blue, and I've actually drawn a dotted line for its maximum value. Sorry, this blue dot is its maximizer, and the dotted line is its maximum value. And there's something kind of telling about this picture, which is that actually the maximum value of the dual quadratic and the minimum value of the primal quadratic coincide. So here, unlike the example we had before, there's a zero duality gap. Okay, so if we were to try to look for the tightest lower bound possible out of the dual, we would get back the primal criterion value at its optimum exactly. Okay, so we're going to talk about that. That's called strong duality. Just as a kind of preview of next time, we can say more, actually. So the reason why duality is so useful and so powerful is that we can go beyond talking about the minimum values of our problems, and we can start talking about the minimizers. That's really what we care about, right? You typically don't care about f star or g star. We really care about the value x star that minimizes the problem. So duality provides us a lens for saying something about that. And the main way we do that is to use what are called the Kkt conditions, we'll talk about later. But just in this example, you can see from inspection that the black maximizer is actually at 0, 0. And I'm going to claim that you could have known that without having to ever form the dual. Why would that be the case? See if, just curious if people could have guessed that. It means the constraint's inactive, actually, in the primal. Right. So this is called complementary slackness. That's what we'll learn when we talk about the Kkt conditions next time. I just was seeing if people would have seen that before. You can see basically because the fact that x1 and x2 are strictly positive at the primal solution, that implies that u1 and u2 both must be 0 at the dual solution. It's called complementary slackness. So just a preview of how the solutions relate. So we've talked about the Lagrangian, the Lagrange dual function, and then we've kind of implicitly been mentioning this the whole time, but here's just a formal statement about the Lagrange dual problem. So the Lagrange dual problem corresponding to that original problem we started off with was just to maximize the Lagrange dual function over all dual feasible u and v, so all u that are non-negative in any v. So that's called the Lagrange dual problem that corresponds to this original primal problem. And this might look like a pretty simple problem. It only has one constraint. But just be aware that oftentimes what happens is when we form the Lagrange dual function, we get kind of constraints on its domain along the way. That's what happens with LPs, right? When we formed this Lagrange dual function, we saw that it was going to be minus infinity unless a constraint was met. And that kind of introduced a constraint into the dual. So oftentimes the dual is going to have a lot more constraints than just the simple non-negativity one. They're just hidden in this G notation here, right? Because G may carry with it domain constraints. So the key property is called weak duality. If G star is the optimal value here, it's the maximum, the biggest we can make the Lagrange dual function over the feasible set, then F star, the optimal value of the primal problem, is always bigger than or equal to G star. And that comes straight from our construction, right? The fact that this is always a lower bound for any u and v that are feasible means that when we maximize it, it's still going to be a lower bound. That's called weak duality. Okay, this always holds, even if the primal problem is non-convex. Okay, you give me any problem you want. If I could form the dual problem, take its maximum, and I compared it to the maximum of the primal problem, I would always have this weak duality relationship, even if the primal was non-convex. Okay? Questions? Yeah, on. There is, yeah. We're going to come back to that when we talk about uses of duality in a few lectures, but the kind of quick answer is that we typically introduce constraints. So we introduce kind of auxiliary constraints in order to form a dual. It's a good question. Yeah?
Is it correct to say like if I got strong duality, then the problem is convex?
No, not correct. So we'll see that the direction of implication goes one way. We'll talk about that in a few slides.
Does the word dual means the original problem is also the dual of the dual problem?
Another good question. So somebody asked me that question, like I think a few years ago when I taught this class, and I didn't know the answer, so I had to go study up. And the answer turns out to be almost always. Almost always when you take the dual of the dual, do you get back the primal problem? I think I have a slide on this again in a few lectures when we revisit duality, but it requires some kind of minor conditions on the constraint functions and on the it requires convexity first of all, and aside from that it requires a few kind of minor conditions on the constraint functions and the criterion. It's always true for LPs. It's always true for QPs. You have a question on your homework which has you prove it for minimizing kind of like a generic function subject to linear constraints. When the constraints aren't linear is when it gets tricky. But the answer is pretty much always yes, I think. It's a good question. So the other types of duality you might hear about is the Fenchel dual and the Wolf dual sometimes. The Fenchel dual is nothing more than the conjugate function, which we're going to talk about in a few lectures when we revisit duality. It's just a different way of viewing duality. Honestly, as far as I see things, all these perspectives are equivalent. It's just what terminology you apply and how you kind of form the dual function. So yeah, I mean, there's no difference between the Fenchel dual and the Lagrange dual. It's just that you happen to call the conjugate of a function the Fenchel dual in a particular context. Another way of saying that is that I think you can use Lagrangian duality and introduce constraints to your problem in different ways to get the same thing you would get from another flavor of duality. Okay, so if you have a problem, you could kind of introduce auxiliary constraints, apply Lagrangian duality, and that would give you the result of applying like a different type of duality. As we'll talk about in a few lectures, the dual problem is not uniquely formed. You can kind of do it in more than one way. These are all good questions. Okay. Yeah, so let me just go through this one fact. It might shock you, and then you can spend the 3 minutes of the break recovering. Here's the key property. The dual problem is always a convex optimization problem. And as written, it's actually a concave maximization problem. It's a maximization problem. Right? So we call that a convex optimization problem. And that's always true even if the primal problem was not convex. Okay, so you give me the most non-convex problem you can think of. If I can form its dual, it's going to be a convex optimization problem. And the proof is extremely simple. Let's just look at the definition of the Lagrange dual function. It's the minimum of the Lagrangian over all x, right, unconstrained. And the Lagrangian is f of x plus the sum of ui hi plus the sum of vj lj. And let me write that just because it's more transparent this way, as minus the maximum of minus this criterion. So minus f of x minus ui hi minus vj lj. And what kind of function is this in uv? It's just an affine function in u and v, right? So for every fixed x, that's just an affine function in u and v. Affine functions are always convex, right? So what am I doing? Ignore the outer minus sign. I'm taking a pointwise maximum of convex functions in uv. So the result is going to be a convex function in u and v. And the outer minus then makes it concave. Okay, so extremely simple proof. Just comes from the property that we learned at the start of the class. Pointwise maximum of convex functions is always convex. So in other words, the dual function is always concave in its arguments, and u bigger than or equal to 0 is a convex constraint, right? Therefore, the dual problem is always a concave maximization problem. Or in other words, we'd call it a convex optimization problem.
Is that one way I can always relax on a convex problem? Just take the dual, take another dual, and then convex.
Yeah, it's a good question. So why is this limiting? Let me see if I can deflect that with another question. Why is this a limit? I mean, I think it's remarkable, but why is it also not that practical, this fact? Yeah, so we haven't quite talked about that, but yeah, if it's not convex, we're going to see actually we can't always say that the dual is tight. So we don't know that. That's a good reason. There's actually a more limiting reason than that, that the primal dual relationship is challenging. Right, it's just hard to get G. So if f was non-convex, and so are the constraint functions, or any of them are non-convex, even if they were smooth, we'd have a hard time getting G, right? Because then taking the gradient set it equal to 0 doesn't do anything for us. So it's typically very hard to form the dual of non-convex problems. If we could, if we were all powerful, we formed the dual, we took another dual, we would get a convex relaxation of our problem, but just doing so may be analytically intractable. Okay, there are non-convex problems for which the dual is possible to form, and there are some interesting ones as well, even where the duality gap is tight. But those are more special examples rather than the norm for non-convex problems. OK, let's take a break, and we'll come back and discuss weak and strong duality.